YouTubers, it's me, your host, Zio. And today I have something special. This is special for the world because I've been kind of thinking about it and saving it for say about 12, 13 years. I've been waiting for the world to kind of catch up with me. But it seems like lead scientists all over the world are all stuck in their like pet projects, I want to say inside their own boxes. How about that? But this is the world's first solar light bulb, a vacuum bulb with a polymer photovoltaic sprayed on the inside. Now, why would you want to do that? Because it protects the polymer from oxidation, environmental effects, and it maintains a vacuum or laboratory condition for the polymer solar cell. Polymer solar cells are very, very, very susceptible to something called oxygen creep. See, with aluminum's kind of weird. If you take you can do chemical, you can do electron spray, you can do a bunch of different ways to strip off the aluminum oxide. See, aluminum, it has this affinity for oxygen. It has this valence shell that sucks oxygen to it, and then it forms the oxygen, like aluminum dioxide layer. It's a transparent layer, but it's non-conductive. What polymers, when you use them in solar cells, can do is they can take that valence attraction, and it's kind of like stacking up batteries. If you stack a battery in series, you change the voltage. You stack a battery in parallel, you change the amperage, the total potential. Well, with aluminum, you can use it as a base plate, and you can put your polymers on top of that. And when you put your polymers on top of that, it takes that valence shell attraction and kind of like stacks it up. It's an electrical thing, like it says, hey, I still want that. And so it creates this vortice or attractive force that kind of sucks in maybe it causes the force to pull the electrons through the p-n junction down to it creates a very strong hole or donor, also called an acceptor. Anyway, so up on the board here, let's just kind of go over what I got because, time is short. Vacuum bulb polymer photovoltaics. I'll just read it out to you. It converts low output polymers into higher output by increasing the surface area that's available in a given space. So unlike normal solar cells, which you're limited to the polycrystalline or the monocrystalline or even the thin films, you're limited to a two-dimensional plane. Using a bulb or glass bulb, you can spray the inside of the bulb in layers using carbon vapor deposition or magnetron sputtering, and you end up with a functional cell. And you can just take a little contact finger grid, or that's what you probably should use, or even just a wire and spin it up, maybe with a little bit of epoxy, silver epoxy, and connect it to the inside. And you might even be able to just solder it like right here at the base, but I just put these in here because I kind of like the idea of the finger grid on full contact. But you don't have to do that. You can just literally just take a little wire and solder it to the inside of the final coating. So you got different coatings inside this proposed solar light bulb. And the first coating is going to be, on the inside of the bulb, is going to be a transparent conductive layer. Now this one's really important. I spent 5 or 10 years thereabouts kind of like researching the best types of transparent conductors that you could use in conjunction with polymer-based solar cells. This is when I was designing and developing epoxy-based solar cells for submission to the National Renewable Energy Laboratories, which they did some testing. I don't think they ever figured it out. But that's okay. Well, maybe they did. We just haven't heard about it yet. Either way, I presented some data on polyisothionephthalene. Polyisothionephthalene is this crazy polymer that forms, you can form like a fibril mat out of this polymer, and these fibrils are 90 nanometers in length, and it is transparent to light but is electrically conductive. And this is also a polymer. So the structure right there that you see with polyisothionephthalene, it's very similar to the next thing that I recommend for the inside coating. I mean, you can use tin dioxide too. I mean, if you can get the conductivity across the surface of the bulb, you're probably going to have to compound that with something else. Because, I mean, if you want to start making these larger bulbs, like these ones over here, these ones These ones I predict will be like the bulbs to have, and that's going to be like a 6-inch diameter glass bulb, or maybe even a 4-inch diameter glass bulb, but it's a really long one, like those vacuum evacuated glass tubes. Well, these are going to be vacuum evacuated glass tubes, but you're going to use the polymer to coat the inside of the tube, and that's going to be, you know, direct power, you know, DC. You're going to have direct current coming from those coatings, which is going to be a step in the right direction, because they do have vacuum evacuated glass tubes that they're using for concentrator solar, you know, where they heat up the oil, and that's pretty neat too. But I think I'd rather have just direct power. It's going to give you high surface area, and you technically only have to coat the front side of the bulb, or you can coat the whole inside and just use a mirror on the back and get an extra 30%. So a 30% collection, not 30% efficiency. Now, the problem with photovoltaics, especially polymer photovoltaics, is their low efficiency. The low efficiency of polymer photovoltaics, that's kind of a crux. It's like it's against like the ability for polymer solar cells to make it into the market, because you can't put enough of them out there. They don't last long enough. But if you, anyways, let's get back to the coating real quick. We're going to go over this, and then we'll go into talking about it. Okay, so transparent conductive layer, you got to use a tin dioxide, polyisothionethylene, or a single wall carbon nanotube matte. Electrospun. And if you ever dealt with electrospun carbon nanotube mats, there are certain processes that you can use to essentially grow a Brillo pad looking stuff of single wall carbon nanotubes, where it's all connected together. So you end up with extremely high thermal conductivity, extremely high electrical conductivity, and you can create a sparse enough matte to transfer that charge. And that's really important when you talk about large surface areas. I mean, there's also a possibility of conversion. Like you could create a electrospun carbon nanotube mat that also takes and converts infrared into some type of potential as well. But that's something you all have to figure out. I can see it in the structure and the math. I'm not going to go over right here, because what we're dealing right here is with the solar light bulb. You know, I want to be able to buy these at Home Depot eventually. Okay, so your transparent layer is on the inside of the glass bulb. The next layer you're going to have is an N-type photovoltaic photoelectron generator, polymer. So there's a bunch of different ones out there. Some of them use dyes, some of them use actual elements. Cadmium telluride is one of those that generate cadmium sulfide. Once again, we're dealing with cadmium. We're dealing with relatively rare or more rare materials, but you could probably also use a phosphorus embedded in an ion epoxy or something like that. So there's another way to do that we could do this, but let's just deal with generalized. We're just generalizing this for the world. We're not going to specify specific things that you should use, but like I said, there's a lot of different polymers, photovoltaic polymers out there that generate, and they're literally like, there's probably 1,000 different ones out there that'll generate a slight potential. Of course, some of them are way better than others, and the dye-sensitized polymers are probably the best from what I've read. But you can use any type, okay? But you got to create the N-type. That's the photoelectron generator. That means that when the light strikes it, it emits photoelectrons. Then you have to have a P-type, which is a hole or donor layer. That's essentially your, hey, come here. And this is usually combined in polymer photovoltaics with an aluminum base plate that's been scrubbed of its aluminum dioxide layer. So you have pure, chemically pure aluminum, you know, from electron gun blasting or however you want to do that under vacuum, and then you apply the P-type with a magnetron sputter or chemical vapor deposition. And it must match the compatible polymer. So you're going to have an N-type and a P-type. The P-type is the acceptor. Now you can beef that up by having the aluminum base plate, and that's where the problem is. That's why this solves the polymer photovoltaics issue. The polymer photovoltaics issue is you have to have some type of boost to get those electrons and to get those layers, the p-n junctions, to function correctly, and that is done with aluminum. It's also done with a couple other things, but aluminum is one of the main things that we're seeing in laboratories all over the world that they're using. So it's not a secret. It's not a secret, but it does behoove us to know why they're using aluminum and why polymer photovoltaics fail. And they fail because of oxidation. They fail due to heat creep. They fail due to oxygen creep. But that's the main thing, is the oxygen creep. So all of those things combined, what's the biggest point of failure? And that's the oxygen creep. So if we put them inside a vacuum now, this is the other thing. Inside the glass bulb, most vacuum evacuated bulbs are like 10 to the negative 3 torrs. That is fine. The polymer will be just fine in there. Everything will be fine. And it keeps the oxygen from getting in there. So once you have the N-type and the P-type, you have a PN junction. And then you have the aluminum base plate, which acts as it's kind of like a dual, like the aluminum base plate with the P-type photovoltaic hole or donor. They work together to pull the photoelectrons that are emitted when the light strikes the N-type and throws out little photoelectrons. And then you have a charge. So if you connect a load or a meter across from the positive and negative, and I wanted to use the standard mogul screw base, just a screw base, you know. I mean, it could be even an insert and twist and lock, you know, like a B and C connector for a coaxial cable. So this is still something that could be improved upon. I think that the B and C connectors, those are great because they're spring loaded and they will maintain pressure over time, and you'll have a pretty good connector. Of course, these ones are pretty good too. So polymer cost is lower than any other solar. You can't even touch polymers low cost with any type of solar, even thin film. Those technologies are so expensive. Polymers are cheap. You can manufacture, and that's the attractive thing. You know, everybody's like in their postgraduate or mid-graduate, you know, type of level, and they're studying semiconductive polymers and semiconductors in general, and then they run into the photovoltaics layer and they're like, wow, I can make free energy out of something that is just dirt cheap, basically out of Glad sacks, you know, I mean, just out of trash, you know, you recycle plastic when you use this. That's kind of like that, but it's a little bit more involved. I mean, like I said, if you want to use, you got to have that transparent conductive layer. You got to have something that's a tunable conductivity or a high conductivity, like a finger contact grid that was what they use on standard solar cells, you know, monocrystalline and polycrystalline. And that's why I was thinking like the single wall carbon nanotube electrospun mat, because you can just go foomp, or you can stick an electrode up in there and just go foomp. You can like literally put, if you flip this thing upside down and you put your pre-powder of carbon down inside there, and then you stick the electrospinning. And you might want to do this in layers. You might want to start with a tin dioxide so you have an attraction, and then you can grow the electrospun carbon nanotube mat to just the right thickness to still allow light through. Because, you know, polymer photovoltaics, they are only so efficient, but they're also very, very, very cheap. They're lower than any other solar. Now, let's go over the reasons why you want to do this. Reasons are, it prevents oxygen creep into the polymer base. It protects polymers from environmental exposure, like I mentioned before. It acts as a heat sink to prolong the life. So this glass, it can also sink it to the bottom. So this bottom piece right here, this could be screwed into an actual heat sink so that the heat that is generated by the glass, you can make the glass just thick enough, and you can use more thermally conductive glass. You could use fused silica. You could use, you know, quartz. You can use a lot of different things that have a higher thermal conductivity, but I think glass will be enough. You can make the thickness just thick enough so that it carries the heat away from the polymer surface at a rate that is high enough to maintain the integrity of the PN junction and the polymer itself. So this is like a bunch of different things going on at the same time, using the vacuum to protect the polymers, and you can use the glass and then a thermally conductive glass and a base plate, the screw base plate, to be able to carry away that heat. So I was thinking with the mogul base that'd be good, because you can like have actual pressure, contact pressure, and this could literally be a heat sink base. Acts as a heat sink to prolong the life of the polymer. So thermal breakdown, you can protect from that. UV breakdown, you're going to protect from that because what? You can use UV protective glass, or you can even put a coating on the outside of the glass to make it so UV doesn't penetrate. So this is going to be like if you put a little bit of more thought into it. I know eventually the bean counters are going to shave it down, shave it down, shave it down. But let's say you had a layer of a coating on the outside of this glass. I'm just going to draw it really nasty and big here. And you put a UV protective layer, UV protect. Okay, you put a UV protective layer so that UV doesn't even make it into there. And you know, UV doesn't really penetrate a glass. I think it reflects pretty well. There are some that allow, I think there's some plastics, but you know, and that could be something else too. Can you have a vacuum inside a plastic container? Not as easily. I think glass works better. Anyway, so UV protective glass, UV protective coating. You can spray it on the outside when you're done with the cell, and you can make that as thick or as thin as you want. You could even tune it. And then you start talking about, okay, so now that we have this junction layer that we can play with, why don't we like coat it with garnet? You know, we can have that tunable spectral layer where we can take the incoming light and tune it to a spectrum that is very, very specific for our photoelectron generator. Now you're talking about a tuned photovoltaic, which is even better. Now, if you wanted to put that coating on the inside, you could too. So, you know, maybe the first coat is that. So now you're going to have a vacuum. You have this vacuum enclosure that you can put all these cool and neat things in it that might be sensitive to the real world out there and need to be behind glass. You know, and you can vary the thickness of the glass. And anyway, so it adds a 3D shape to the cell. That's one of the important things about this design, is that you can create these three-dimensional shapes, and you can now start playing with things that you can't do with monocrystalline or polycrystalline solar cells, because you can't do that with that. These are great. You can make it look like an elephant. You can make it look like, you know, anything that is a shaped, blown glass shape. The inside of that thing can be solar cell. And now you're talking about like yard art and you know those globes they have in the gardens, the mirrored globes? You could have those. Those would be cool, right? Imagine those things just like all throughout the garden. I mean, those things would be cool, and they all produce power, right? So now we're talking about a brand new type of solar cell, and it's cheap. You're talking about really cheap compared to growing crystals. I mean, and then sawing them and polishing them and treating them and blah, 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 blah. Gets rid of all of that. So you have ultra low cost photovoltaics. Now, the different ideas, of course, about the 3D shapes is you can now explore, like these are long bulbs with micro mogul bases, and of course a heat plate there to carry away the heat. But you can now have this, you can create light traps, like on a macro scale. Instead of a nano scale, you can now have this macro scale of a light trap, and that's essentially what this is. And let me just write that up on here on the board. This is a light trap. You see this right here. It funnels the light in, and you can change the. You can make it so it opens up this massive world of design. It does. It just, you can now do all this cool stuff like all the pyramid shapes and all the different things that all these researchers have been wanting to do, and they want to be able to do it with monocrystalline and polycrystalline cells. You can see it in their designs. They really want it. But if you had an inexpensive solar light bulb, if you had an inexpensive, and when I say inexpensive, I mean it. These things are going to be cheap, and they're going to be durable enough to ship anywhere. It's not like the super fragile, like monocrystalline and polycrystalline cells that just break so easy. Now, admittedly, we're dealing with glass, but those things are so breakable. So let's look at this, and we'll decide what we're going to do with this. And as a species, as humans that need more power, we need more power. We need vacuum bulb polymer photovoltaics out there in the market, out there in the world, as soon as we can get them, because there's not enough power. I mean, we consume power so... everything in our lives takes power. This thing takes power. Everything takes power. And we need more power. And it needs to be in a form that'll last. I think that as long as the vacuum is maintained, this PN junction should be stable. If you take all the other things into account. Like, for example, the heat sinking thermal capabilities, and if you really put some thought into this design. And like I said, there's like 1,000 different polymers out there that will produce a photo, and admittedly there's not as many elements, but polymers are really cool. What's nice, all you people out there looking to get rich on polymer photovoltaics, it can happen to you. You know, like I said, there's so many different polymer photovoltaics, and dye sensitized. Admittedly, dye sensitized, those are very specific things. Those are actually more expensive. Let's go with the simple stuff. Let's go with the stuff that is almost working, and they're trying to roll it out on plastic. And of course, you get oxygen degradation, you get UV degradation, you get all these things that take polymer photovoltaics and shove it to the back burner, put it up on a shelf. Oh, well, that was great. We spent, you know, $1 million on that, and you got a bunch of solar cells that are going to last, what, a year? Okay, so that's a problem. You need to be able to encapsulate and enclose the polymer photovoltaics so they're protected from the environment so that they'll last. And you need to take thermal runaway. Cascade runaway is a huge degradation thing to plastics. Plastics warp, plastics fall apart. Admittedly, you add oxygen and you get even more of that. So the top researchers in the world, in Australia, in Ireland, in Denmark, in Germany, and there's even maybe one or two over on the West Coast here, West Coast and East Coast, because there's University of Washington and there's, of course, your Ivy League schools. They're all trying to solve the polymer photovoltaic equation. And the polymer photovoltaic equation is missing something, and that's vacuum. You have to vacuum encapsulate polymer photovoltaics and keep the oxygen from getting to them. Now, there's a flip side to this, which might be able to increase the polymer photovoltaics in special cases. There's this design on the board, but there's a couple others that I've been thinking about, where you could inject a pressurized gas, because we're dealing with a light bulb enclosure. You can now use special gases, and instead of using the aluminum base plate, perhaps you'll use a special gas on the inside that maintains a higher conductivity to the PN junction, which actually adds, because you're dealing with a nanoporosity to the polymer, and you could even induce micro porosities by using electrospun carbon nanotube mat. And now you can flood it with a gas, and now you have this other range of products inside this little petri dish. It can be pressurized, it can be vacuumed, but now in the pressurized sense, now we can add very, very specific gases to that will change the properties of those polymers under pressure. So now we have this, things that wouldn't work before because you had to have them at 1 atmosphere. When you increase the pressure, you can now have special polymers that before were not photovoltaic, but now will be, especially with the addition of special gases to induce that photovoltaic nature, or induce a conductivity where before none could exist at atmosphere. And that's one of the problems with polyisothionyphene, is it does have an oxidation creep factor as well. All your polymers are going to have an oxidation creep factor. Eventually, they're all going to fail in atmosphere. So you need to put them either in a vacuum evacuated chamber or in a pressurized chamber that augments their conductivity. So now you can have augmentable polymer layers, whereas before you didn't. So yes, you have vacuum bulb polymer photovoltaics, but at the same time, because we're using a chamber, you can now have pressurized polymer photovoltaics. So like I was saying, you can now have pressurized. It's not just vacuum, you can have pressurized. And that's a brand new, I've never seen any, not even one, white paper or blurb on the entire internet about pressurized polymer photovoltaic layer systems. Never have I seen it, but I know it would work. There's all kinds of pressurized bulbs. You can look them up. If you're like a light bulb aficionado, if you really like studying light emission systems, look up pressurized lights. Pressurized lights, they use all kinds of weird gases, and that's a known set of sciences. There's all kinds of books and papers that you can look up about it. And that creates a brand new field of science. A brand new field of science I've never seen. Pressurized polymer photovoltaics with dopant gases. I wonder what you could create. I wonder what you'll make. It's amazing when you think about all the cool things you can do with science. I love science. Science is great. It's one of my favorite things. Now let me step aside so you can get a little picture here. I mean, I'll leave the picture at the end, but imagine the potential. Imagine the potential of this, just as a vacuum bulb polymer photovoltaics. And now we flipped that just a second ago, and now we have pressurized polymer photovoltaics inside a container that light can get to. So, wow! Wow! Look at that! We made brand new stuff, me and you. If I hadn't made this video, we probably would have never come up with it, because who thinks about that, right? Exactly. Well, I hope y'all have this is probably let's say 100 of you out there right now watching this video are going to carry this torch to the finish line. you're going to make money. You're going to get your doctorate. You're going to save the planet by giving it more power. You need more electricity here. We have this unlimited source of light out there. It's called the sun. And all we got to do is figure out how to harness it. And polymer photovoltaics, they probably will show us that we don't necessarily need as much of the rare earths to be able to really accomplish the goal. I think, and we won't need the furnaces, the diamond saws. I mean, they can still make they're cranking out gigawatt, megawatt, multi-hundreds of megawatts, thousands of megawatts of standard solar cells out there right now. I think that there's enough leftover light bulb vacuum machines out there that are just literally sitting there. They built them, they used them back in the day. Now everything's LED. However, this is a use for those. So you could probably pick up that equipment for cheap and start this whole ball rolling. Edison, are you listening? Southern California, Edison. There you go. New light bulb for you. You know, imagine if they had solar light bulbs back in Edison's time. Now, admittedly, they had a little ways to go because polyacetylethane, that was, say, 20, 25 years ago. And electrospun carbon nanotubes, that was more like 10 years ago. And tin dioxide, of course, that goes back to the beginning of transparent. So this is all a timeline, and there's probably something new. Actually, we added something new today, didn't we? We added something new, so we're gonna title that today. We're gonna title it because that's what we do. We're scientists, and we made a discovery. Me and you here on YouTube right now. There was a discovery, and it was made today. And what it is we're gonna call this. It's we'll call it high pressure. High pressure polymer photovoltaic cell. HPPPC. Yeah, high pressure, and that's and we saw what it was. It's just, you know, we'll draw a little diagram here. Basically, you have the coatings on the inside, and then you have a pressurized gas, or you have pressurized gas on the inside, and that changes the intrinsic properties of the PN junction, and you end up with, you notice how I drew it with like really thick glass here, right? Because, you know, it's gonna be thick. And on the inside of that marble, these are gonna be, we call them solar marbles. Solar marbles. I know there were other solar marbles, but these will be the cool solar marbles. These are the ones you can charge your phone with. So you can have these solar marbles that you create. Solar marbles are really cool. I mean, this could be a thing. This could be a thing. Why aren't we making this stuff? Oh, that's right, because I just introduced it today. Well, thank you for watching. I love all of you scientists out there that are watching my videos and learning how to change and shape the future of mankind, because it's the love of life. It's the love of being able to create, like the last video. Last video I made was the lowest cost shipping option pretty much available by the mile. And that was your Continental, delivery cannons. This one, this is the lowest cost, highest output, most renewable energy that you can pretty much do. I mean, this is polymers. It's carbon, hydrogen, carbon and hydrocarbon magic is essentially what this is. And this is a brand new kind of magic. We have low pressure polymer photovoltaics. We have high pressure polymer photovoltaics. And that's like, we could have entire universities around just what's on the board behind me. Speaking of which, I gotta get going. But I thank you all for watching my video. Be sure to subscribe and like and encourage me to keep creating this stuff and bringing it to the internet and bringing it to the world. Because the world needs more power. It needs more options that it didn't have before. It just didn't have them. And this is a great example of science that you won't find in a book. You're going to have to read like a whole bunch of books to get what's on the board here. To really understand it. But here's my advice to you burgeoning scientists. If you want to make projects like this, go out and get your degree. Finish your degree. Go to your colleges. Finish your degree. Listen to your parents. Listen to your professors. Go out there. Get the biggest and baddest degree, awesomest degree you can get. Get a chemical engineering degree. Get an electrical engineering degree. Get your big bachelor's degree and then realize it's not big enough. You need a master's degree because you're so specialized and you want to save the world, just like Zio. You want to save the world. You want to create solar light bulbs. You want to create the next generation of transportation systems. You want to create all these things and help mankind reach the future, because it takes a lot of work and it takes a lot of people and it takes a lot of thinkers. Oh, also, you thinkers, watch your backs. It's a dangerous world out there. Look for cars, look for bad food. Keep yourself healthy so you can reach the future and share your ideas with other scientists, with other people that are thinkers, that really want to do the same thing as you. This is a future that is only made possible because of things like PBS. I'm the product of PBS. You want to see how PBS works? I am proof that PBS works. All those Sesame Streets, all those things. And then, of course, it moved into other books. But, I mean, you go all the way to the back of where we begin learning and why we want to interact with people at all. And it's these social interactions that allow us to share these things. So I'm presenting this to the world. I think we need it. I think we need more power. And we need a solution to the monopolized situation with, you can only have solar that's effective with, polycrystalline or monocrystalline. We need a solution, and this is a solution. Solar light bulb. The solar light bulb! Can you believe we have a solar light bulb on the board? I cannot believe this board. It's beyond me. Look at this thing. It's wow. Actually, it's not beyond me, but I mean, it's from me. This is the type of thing I think about all the time. So, if you're ever talking to me, and I seem kind of like I'm distant for some reason, it's because I'm thinking about stuff like this. And a thousand other things. So, but I want to thank you all for tuning in. Again, thank you for tuning in. And it's important to me. As a creator, every little like, every little view, every little thing that you do out there encourages me to make more content like this. So you can, like I said, there's probably at least 100 of you that's going to carry this torch, one of these torches, forward, and you're going to have the opportunity, because like I said, it can be there's a whole bunch of tunable polymer photovoltaics, and you could probably use thin film on this too, on the inside. So there's another one. So this is vacuum polymer photovoltaics, but it's also thin film. So we're going to go or thin film or thin film. Okay, and that just opened up 100 other doors. So having an encapsulation technology and having high pressure photovoltaics, I think I haven't seen that, and I definitely haven't seen this. Go out there and change the world, make it a better place. Save the world through solar power. Every chance you get. Solar power, 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 solar power. It's like a train. Solar power, solar power, solar power. And that's me. Take it off.